Swayam Prabha. Digital India. Educated India.
In the last lecture, we basically derived a relationship for mass flux for a particular species with respect to stationary coordinate system, right. For a methane, right, this is mass flux is equal to YCH4 into mass flux minus rho d CH4 minus S2 and dy CH4 dx, right. Now, I couldn't really cover in the last lecture something which need to be discussed now, right, because this is very important to appreciate the mass transfer process, right. And similarly, of course, I can write down for that hydrogen is equal to hydrogen m dot minus rho d hydrogen CH4 dy hydrogen dx. Let us say this is I am considering now as equation 1 in this today's lecture, right. We will have to look at what is happening to this bulk flow, right. Let us have for that let us have a better feel of the bulk flow and the diffusional fluxes, right. If you look at these are the basically diffusional fluxes, this thing is known as fluxes for methane, right. This for methane and similarly for hydrogen in equation 2, right. Let us consider total mixture mass flux, right, mixture mass flux, and this mixture is binary in nature, right. What is that? That is basically m dot double dash is equal to CH4 plus m dot hydrogen. What I will do? I will basically use this equation 1 and 2, right. So, what is that? YCH4 minus rho d CH4 S2 dy CH4 dx plus y hydrogen minus rho d H2 CH4 y hydrogen by dx, right. So, if I will add this together, what it would be? What it would be? I can write down this as YCH4 plus YS2. Yes or no? Can I not write down this portion? And that YCH4 plus Y hydrogen, what is that? 1, right. That means you can note that YCH4 plus Y hydrogen is equal to 1, right. That we know for a binary mixture of methane and hydrogen. And then I can write down this as m is equal to, this portion will be becoming what? M dot is minus rho d CH4 hydrogen dy CH4 dx minus rho d H2 CH4. So, this will cancel it out, right? Yes or no? That means this term, total diffusional term is, mass diffusional term is 0. Yes or no? Right? That means I can write down this as, right, rho dCH4 hydrogen dy CH4 dx minus rho d CH4 is equal to 0, right. And this is for the binary mixtures. You can also derive that basically for what? For the IS species, right. And for what is this thing? This is basically mass flux due to diffusion. So, for NS species, right, summation of m dot I, and this is I am saying diffusion, okay, I is equal to 1 to n is equal to 0. That means this is basically is what you call the total mass flux is equal to 0 for what? For the diffusion. That means total diffusional mass flux will be 0 in a mixture, right. Therefore, the bulk will be coming, like are you getting? It's a very interesting thing you should appreciate. That means somebody will be moving fast, somebody will be moving slow, altogether diffusion will be not affecting the bulk flow. That is very important point I am making. And this is due to only molecular diffusion, okay, or the due to the, you can say, but there will be some thermal diffusion, and this diffusion, whatever I am talking about equation 4 is basically for what? Concentration. Due to concentration gradient there will be molecular diffusion. There will be also some molecular diffusion due to temperature, that is thermal or the Soret effect. There will be also the Duffer effect. There will be also pressure diffusion, all those things will be there. We are not considering, we will be not considering in also later on, because it is quite complex in nature. But however, when you do actual modeling, particularly using the computational tools, you will have to consider at least Soret effect in the combustion whenever you are taking the hydrogen oxygen system. You cannot afford to say no, okay, otherwise things won't be good, prediction won't be good. So, with armed with this expression, particularly keep in mind that equation 3 and also it we will be using, and for IS species we will be using, and we will be now using this for deriving the species conservation equation, right. Let us do that. So, now what we will be doing, basically looking at the species transport equation. We will be deriving this, right. Let us consider that, I mean, as usual we will take a infinitesimally control volume in a 2-dimensional situations. This is 0 0 and this is delta x 0 and delta x delta y, this is 0 delta y, and this is in x direction, this is in y direction, right. We are taking infinitesimally control volume. This is our control volume, it is having phase A, B, and this is phase C, and this is D, right. This is our control volume basically. Now, what we will have to consider? We will have to consider for IS species, right. We are considering IS species. That means the mass flux, mass which will be entering, mass flux will be what? for due to the ith species is this much, okay. And what will be coming out of here, and this is in x direction, right. We will be also considering x direction plus x into delta x, okay, right. This will be delta x. Now, in the similar fashion in the y direction, right, in the y direction this will be ith, okay. I means ith species, okay, y mass flux So, these are the things we are doing, but we will have to go back to the main things. What is that? This is the basically species conservation, and species conservation, if you look at, we know the rate of ith species mass accumulation is equal to rate of ith species entering into the control volume and rate of ith species leaving the control volume, right. Plus what it would be there? There will be mass production or consumption of the species, is not it? There will be something which we did not consider in the last lecture. So, now then only we can look at this conservation. So, let us consider, let us carry out mass balance for ith species. Ith species means it can be methane, it can be hydrogen, it can be anything, like if it is a binary mixture, it will be methane and hydrogen. So, that what is that? That is basically rate of ith species mass accumulation is equal to rate of ith species entering into species mass, right, into CV minus rate of ith species mass out of CV plus production and destruction, okay. I am just production and, okay, should I write destruction also? Of ith species mass in control volume. Keep in mind that this equation is what we call 4 or 5, just check, 5, 5. Make sense? Now, what is this rate of species of mass accumulation? Rate of ith species mass accumulation in CV will be rho yi into delta x into delta y into, of course, 1, therefore volume is taken k, right. And rate of ith species mass entering into CV along what, x direction. What it would be? It will be x into delta y, isn't it? This along with this phase A, and rate of ith species mass out of control volume along x direction will be Ix m dot Ix into delta x into delta y. So, if you look at net rate of ith species mass, along x direction, what it would be? It will be nothing but I have done earlier same thing. So, it will be minus dou by dou x m dot x delta x into delta y. Yes or no? Is it okay? And similarly, net flux, net rate of ith species mass along y direction, what it would be? It will be minus y m dot flux I y delta x into delta y, right. Mass of production of ith species is basically in CV, what it would be? Into I delta x delta y, right, into 1 basically, right. Now, in equation 5 all the terms we have derived. If we will just include that in the equation 5, right, if I say this is, maybe I can say this is your 6, this is 7, 8 and 9. So, using equation 6, 7, 8, 9 in equation 5, right, I can write down that as equation 6, 7, 8, 9 in equation 5, we can have rho y I dt plus I x dx plus I y dy is equal to this is equation 10, am I right? So, if you look at what is this term, this is known as source term, right, and how we will get this thing? you know, we have already derived that from the chemical kinetics, right? We can find out what it would be using Arrhenius laws and other things we have derived. You remember that? So, now this is a non-linear in nature. This will be non-linear in nature because it will be dependent on the temperature, dependent on the other factors, concentration, because you do not know that. Now, coming back to this, right, we have already derived a relationship for mass flux of IS species along the x direction, right. Right, that is mass flux of IS species along x direction, what it would be? yi m dot I x minus rho dij right. This we have already derived, and similarly mass flux of IS species, similarly the mass flux of IS species along y direction would be and keep in mind that these thing, if I consider, what is this one? Any idea? This will be nothing but your m x, which is nothing but your rho v x. Yes or no? Similarly, if I sum means this is I is equal to n, all the species. If it is binary 2, if it is whatever the number 10 species, you are considering 10. So, this also will be equal to m dot I y is equal to rho v y. Yes or no? Right? So, what I will write down? I can write down here itself as y I rho v x minus I j dx. Similarly, I can write down rho v y minus rho dij. Let us say this is 11 and this is 12. By using equation 11 and 12, in equation 10, we can have plus y dij y by dy plus this is sum. Keep in mind this 3 dash means per unit volume, okay, that you should keep in mind. Now, this is your expression for IS spaces. Are you getting? And what is saying? This is basically the unsteady term, this term is unsteady, and this is mass flux of IS spaces along x direction, this portion, right? Right. This is mass flux of IS spaces along x direction. Of course, the similar thing is here, this portion, right, and this is due to diffusion, right, this mass diffusion term along x direction, right, gradient, diffusion gradient basically. And this is a source term. And this is the mass diffusion along the y direction. This is basically mass diffusion in y direction. So, for axisymmetric, the species conservation equation would be geometry. We will be using basically what we call RZ theta coordinate system, but however we will be considering RZ. Okay. The species equation becomes I by dt plus 1 by r dou by dou r rho v r y I, right, plus I equal to dz rho di j y I by dz by r rho r di j y I by dr plus m dot dash I. Keep in mind that this is a thing, and generally this what you call axial diffusion, that means z is your axial, right, z is your axial direction, that is very small, right, is neglected as compared to what, radial diffusion. This approximation we will be making in whenever we are dealing with what you call jet diffusion flame, because jet diffusion flame will be using this axisymmetric equations. So, therefore, it is very important to look at it, and similarly you can write down for spherical coordinate system also. Yes.
Triple dash. I am got triple dash.
Triple dash. Yes, right. This will be okay. Thank you very much. We will stop over here, and in the next class we will be discussing about energy equation and also a little bit about terminology about turbulent flow, and then that will be the end of your this thing. Okay. Thank you very much.